Good morning, everyone. We heartily welcome back to the second day of the FDP program. Let us welcome today's first speaker, Dr. Shashi Bajaj Mukherjee, Department of Mathematics, Dr. B.C. Roy Engineering College. Presently, Assistant Professor of Mathematics in the Department of Basic Science and Humanities, Dr. B.C. Roy Engineering College, Durgapur. She has completed her bachelor's from Bardwan University, master's and PhD from Jadavpur University. She has done a one-year postdoc from IISc Bangalore in the year 2017. She has 16 years of teaching with 7 years of research experience. She got the Young Scientist Award in the year 2010. She has published her research papers in reputed peer-reviewed international national journals and also attended several international and national conferences and published her research works in the conference proceedings. Her present research interests are biostatistics, soft computing, and numerical simulations. She is enlisted as a registered PhD guide in Macaut. She is a lifetime member of ORSI Durgapur chapter and other organizations. Apart from this, she has successfully completed her role as a translator and recently associated as a validator for SWAYAM courses in AICTE. To brief about our today's session, we are going to learn about Mathematical Foundation 2, Linear Algebra and Vector. We now hand over the session to Dr. Shashi Bajaj Mukherjee. Please, Madam.
Thank you, Ria. I hope I am audible.
Yes,
Am I
madam.
audible?
Yes, madam.
Okay. Okay, so first of all, let me share my PPT. Okay, so is it visible?
Yes, absolutely. Yes, madam, your PPT is visible.
Yeah, let me make it a full screen. Now I think it is visible, no?
Yes.
Okay, so thank you, everybody. Wait a minute. So first of all, a very nice good morning to all of you. And I want to give the thanks to the organizing team for organizing this wonderful faculty development program on the data science and its application. My today's topic, so slide is changing, no?
Yes, ma'am.
Okay, thank you. So our today's topic is mathematical foundation on linear algebra and SGT. Myself, Shashi Bajaj Mukherjee, Assistant Professor Mathematics from BCRAPC Engineering College. And on our yesterday's session, there was a mathematical session, and there we got to know about the probability and statistics, and that is of course the first pillar of data science. Can just let me take a minute, okay? Okay, so that one is the first pillar of our data science, because we are going to, that is, we are here to understand the data science in light of the mathematics. That's so why I am taking the topic here, linear algebra and the SVD. SVD is generated by the linear algebra, but it is the most powerful one more pillar of data science, I can say. So about the linear algebra, we can say is that linear algebra is like the superhero toolkit for the data scientist. It helps us handle and make sense of big, messy data sets. Think of it as the math magic that lets us play with vectors, matrices, and transformations. In simpler terms, it is the backbone behind the cool stuff we do in data science, finding patterns, making predictions, and uncovering hidden insights in heaps of data. So, linear algebra is our secret weapon for conquer the data jungle that we can see. So I hope you can understood that the linear algebra is going to be a very, very important topic for the data science. And for that, the today's lecture bullet point is overview of the linear algebra, visualization of matrix, transpose and inverse, determinant and symmetric matrices, eigenvalues and eigenvectors, positive definite matrix, spectral decomposition, singular value decomposition, and the problem solving and application of FDD. So I have taken the very basic topics from linear algebra, but definitely in a different dimension so that we can apply our this knowledge of linear algebra in the data science. So now, first of all, linear algebra means without matrix and vector, we can't. It is the linear algebra. Matrix is the first topic which comes in our mind. So, what exactly is the matrix is? Is it just a box of numbers, a collection of vectors, or mathematical object, or linear transformation, or just a function? So, to get the answer of this question, we have to go through this lecture. So, first of all, perhaps no one of these answers, that means what is the matrix, that answer is perhaps different for the different bodies. But we do know how to multiply the matrix and vectors. So here just have a look. This one is a vector 1, comma 2, and this one, the yellow arrow, is the positioning of the vector 1, comma 2. And one matrix I have taken, that is 1, 2, 2, 0. So that matrix with, we know how to multiply a vector. So if we multiply the vectors, then we shall find out the another vector, that is the 5, comma 2. So that 1, comma 2 is this vector, and after the multiplication of a matrix, we shall find out the vector goes to this 5, comma 2 point. Is it not? So what happens actually? If we multiply a vector by a matrix, then it will transform the vector into another vector. So this is the visualization for one vector only. So what about if there are so many such vectors in the plane? This one is a plane. Sorry. Just a minute. So this one is our plane. Here, not only this one vector we have, but there are so many, in fact, thousands and crores of vectors are there. So our goal is to visualize matrix. So we would think what happened to all vectors as all of them gets multiplied. In our computer can try its best to draw many arrows on the screen to create the illusion of every vector, just like here it is. Just have a look. Just here, one vector is given. Let me take a thing. So likewise, 1, comma 2, there are so many vectors we can draw. Is it? So there are so many vectors, not necessarily from this point, but some other points also. So there are so many vectors, and while we multiply all those vectors with this matrix, then definitely it will transform the vector some other points. So this vector, suppose it will goes here, this vector, suppose it will goes here. So in that way, we will have the different vectors. So a visualization of matrix in this, that means all those vectors, if we want to visualize here, then it will looks like a very messy type of thing. That's why what we will do, we just compress this entire area. That means if we want to visualize this all vector for what the things are going on, we do two things. So what the things we can do, we can at first define our focus region. At first we can define our focus region. Suppose we define a region over here, and here only whatever the vectors are there, we just plot only, we just deal with those vectors only. And what we can do is that next, instead of the arrows, we can put the vectors like a dot. Instead of the arrows, we can just put the vectors like a dot. And after that, based on that, we just do the visualization that what it will actually does. And if we want to visualize that properly, then we should create the visual engine, you can say. Any matrix is there, a vector is there. If we do the vector, that means the transformation, then what will be the changes over this region? Suppose this is our defined region. So what will be the changes on this region that we will going to experience now? So for the different type of matrices, we know the basic different matrices we know, and for each and every matrix, if it will apply on a vector, then what will be happen, or what will be the changes over the transformation that we shall at first visualize. So it is the thing which we will do first. So I can say that I'm just welcoming you all in the world of matrices now. So the first here, the identity matrix. I hope everybody of us know the identity matrix. So identity matrix means it is diagonal entries are 1, and all the off diagonal entries are 0. So if identity matrix you have, then and it will apply any of these vectors. Here the so many vectors are there, any of its vector. If we apply the identity matrix, then what happens? Let us, for simplicity, suppose A comma B, or this one is a generalized vector, let us say. So if we multiply with the identity matrix, then obviously everybody of us know that it is again the matrix itself. That means there is no transformation. Better to say, there is nothing. It will do nothing. If we multiply a vector by a scalar matrix, then it will have no change registered. So whatever be the shape with we are started, the same shape we will retain with. Now, if we come to the scalar matrix. Scalar matrix means it is just a little bit change in the identity matrix, and that is we just multiply all the diagonal entries by the same scalar quantity. So this is a fourth order, this is a third order scalar matrix, likewise the second order scalar matrix also we can have. So here, if with the scalar matrix we consider, and with the scalar matrix if we multiply any matrix here, suppose it is 1 comma 2, or suppose it is the 2 comma 1. Let us consider 2 comma 1. This is another matrix here. So 2 comma 1 means we can take 1 2 comma 1. So 2 comma 1 is this point. So this one is the vector basically. So now if we multiply, if with this matrix, this is the scalar matrix, then we shall find it out as 4 comma 2. So this matrix we will register. So 4 comma 2 means it is the point, this one. So what happens by the scalar matrix? When a scalar matrix applied to the vector, then it will scale the vectors uniformly and making the things bigger. Here just have a look. If we multiply this, then the shape will be bigger. Here one I want to know, or if I just want to ask you that here initially our just have a look. Initially we have this picture, and now this multiplication becomes this one. So now can you tell me how much magnification will be here? How much magnification will be here? If we just visually observe this one, then definitely I hope you can see. But calculation, if you want to do, here the area of the previous region, I'm just drawing the previous region is from this point to this point. So this much, I'm drawing very badly, but so this one is our previous region, and after this multiplication, this region becomes bigger, and this area, suppose this one is the area of this region, and what about the entire region? In fact, whatever be the transformation for a particular region, what should be the area will be there, that we can find out by matrix itself. If this one is the matrix, this one is the matrix, and it is applicable on the vectors of this region, then the entire region, what we shall find out, it is the 4 times of the previous region. So it is the previous area and it is the new area. So this is the new area. And how to find out this area, you know? I hope this one is a square matrix, and its determinant value, I hope everybody can calculate, and it is very simple, and its determinant value is 4. So if AD area is multiplied here, the after transformation, what will be the change in area, that we can find out by multiplying the multiplying the previous area with its determinant value. That is the significance of determinant. I will come later on again on the determinant, but right now I'm just relating this determinant value over here. So this is our scalar matrix. Next here, previous one, it makes the area bigger, and if our scalar matrix is here 0.5, then it will definitely squeezes the area, or the area becomes the smaller. And of course, you can understand that how much smaller the area is, and its determinant value is how much? It is 0.25, so that is 1/4. So whatever be the previous area is there, after this transformation, your area of this region will becomes the 1/4 of the previous area. So now here another type of matrix, that is the identity matrix, but off by one entry. Identity matrix off by one entry means this is all the elements in the diagonal are 1 and off diagonal elements are 0. But in the diagonal, one of the entry is not equals to 1, but rather than 1, it may be anything. Definitely not, it is 0. If this type of matrix is there, then what happens? Then just have a look. Suppose our matrix is 1, 0, 0, 3. Then what happens? It will scales only the y-axis. Again, suppose here it is the x value is 0.5 and y value is 1. So it will only scales the x-axis. So what it will do? It will not. That means this scale, actually this matrix scales just the one axis, and the other axis remains unchanged. Here it is 2 dimension. If it is 3 dimension, then also 2 dimensions will remain unchanged, and only 1 dimension will scale or squeezed. So here the previous ratio definitely not preserved. And one more thing, just have a look here. This one is again a scalar matrix, but one negative entry is here. This one is a matrix, scalar matrix definitely, with one negative entry. If that type of matrix you shall find out, then it will do what? Here the transformation for it will just reflect the entire thing. Here just have a look, the previously this yellow and green color are in this side, and these two colors are orange and red colors are in this side. But now after applying this matrix as a transformation, we shall find out it will revert. So with respect to the y-axis, it will rotate. And similarly here, if we have this matrix, then with respect to the x-axis, it will transform. Just the reflection of the original figure we shall find out here. And it can be possible that your matrix may be where both the diagonal entries are negative, and that time first this flip and the second this flip. That means by combining these two, what will be your final region? That we will find it out. So now it is the diagonal matrix. That is the another kind of matrix. So diagonal matrix means here definitely the diagonal entries are all different. If we consider the diagonal matrix, then you can find out this one is another diagonal matrix. So diagonal matrix is basically the combination of 3 multiplications, we can say. If here it is the negative sign, then only this matrix will be included, otherwise not. And here for this one, we can just divide this matrix. That means this matrix we can split as, here it is the scale by x-axis. That means only the x value we will take here, and y coordinate we keep as 1. Then this here. Then the next matrix, that is the 0.6, which is here, and this will keep as 1, and here we multiply it this one. So I hope these all matrices are known to you. These are definitely, this is the identity matrix but off by one entry. This is also the identity matrix off by one entry, and this one is the scalar matrix with negative entry. So all those matrix for, you know the transformation. So their multiplication is this one, which is a diagonal matrix. And if we do the visual effect of this one, then definitely if we apply this one, then it will be stretch the x-axis, that it will stretch the x-axis. This will squeeze the y-axis. This will squeeze the y-axis, and it will rotate. And if we combine these three, then the combined part is this picture. So next, one more vital matrix, that is the zero matrix, and everybody knows this zero matrix, but it have a very big significance. So what happens if we multiply any vector by the zero matrix? If we multiply it, then any vector multiplied with a zero matrix will convert it to the zero matrix only. So it will moves all the dots to the origin. It will moves all the dots to the origin. So we can think of the zero matrix is just like a black hole, which will squeeze everything within it. So next it is the sphere matrix. So sphere matrix is what? Sphere matrix means here all the entries are 1 and 0 only. First of all, definitely it is the scalar matrix, not scalar matrix, it is the identity matrix where all the diagonal entries should be 1, and in the off diagonal at least one of the zeros should be 1. So just have a look, this one is the identity matrix, and with that here this one is the one entry. If this one we think of, then this is the diagonal entries, and beyond that the off diagonal in at least 1, 2 or more than that will be 1. So then that time it is called the sphere matrix. So in the sphere matrix, what happens, how it will changes the object. So just have a look here, sphere matrix means it will just planting the object. That means it will change the shape of the object, but it will preserve the volume or area, whatever volume if it is in 3 dimension, and area if it is in the 2 dimension. Just have a look here, just whatever be the previously that one is the position, and after applying this matrix it will just slanting a bit. So how it will work for this steering can be possible only in 4 ways, either with respect to the x-axis in the positive direction or in the negative direction, and similarly in the y-axis it is either in the positive direction, that means with respect to the y-axis it is in the positive direction or in the negative direction. Now, sphere matrix and scalar matrix, there is a very small difference, actually a big difference. Sphere matrix means it will change the shape only, but itself preserves the area. And in the scalar matrix, itself preserves the shape and it will change the area. So that is the difference between the visualization in the sphere matrix and the scalar matrix. But all those transformations are very, very important. Now, a very important matrix, that is the orthogonal matrix. So, orthogonal matrix, I hope you know that the two vectors are perpendicular to each other, then it is the orthogonal matrix. So, orthogonal matrix means if we visualize the transformation, then it is just a perfect rotation. Perfect rotation means here no shearing, no scaling, no stretching, no reflection. So nothing will be there, only the simple rotation we will recognize here. And the orthogonal matrix means we know that its dot product definitely 0. Our matrix are 1, 3, 6, 2. So if we take the dot product of these two, then definitely it should be 0. And that's why we say that the two vectors are perpendicular to each other, so that the dot product is 0 if the matrix are the orthogonal. And orthogonal means if these two vectors, if we plot, then definitely the angle between them is perfect 90 degree. So next we come to another matrix that is called the projection matrix. But before go to the projection, okay, here one more. These are some more changes will be given for the orthogonal matrix. So for orthogonal here, the around the z-axis, what should be the transformation? Around the y-axis, if this is the matrix, then what should be the rotation? around y-axis. Here it is probably the 45 degree. It is also through 45 degree, and it is through 60 degree. So these are the rotations through x-axis, y-axis, and z-axis around if these are your matrices. And if we multiply these two matrices means this one is a matrix through the z-axis where it is rotating, and this one is a matrix where through the x-axis it is rotating. And if we multiply these two, then we will get this matrix. And accordingly, this is the visual effect of this one. So if we multiply these two, then its composition is some another. At first, it will rotate through 60 degree towards x, then after that through 45 degree towards z. And if we just interchange these two, that means if we at first do this transformation and after that this transformation, then what happens? Then it will be something else, not the previous one. And that is the reason we can say that the matrix multiplication is not commutative. Actually, what happens, it is the sequential transformation. Matrix multiplication, we can say it is a sequential transformation. So that if we multiply at first this matrix and then this matrix, then its direction or its final transformation will be not same. Well, when we multiply at first the z, that means this matrix, and after that this matrix, so it will change. And that is the reason we can say that the matrix multiplication is not commutative. Next, it is the projection matrix. So let us come to the projection matrix. In the projection matrix, before to know the projection matrix, we should know the vector subspace. So what is the vector subspace? So for any subspace, it should not be an empty set. First of all, the 0 is a vector which should be included in the vector subspace. And the other two properties are, it is the closure under addition and it is the closure under scalar multiplication. I'm not elaborately, I'm not elongate this part because hope all those things you know. I'm just giving you the visual effect of all those things. So just have a look. Here what happens, if suppose a line is given, if a line, that means a vector given on where all the vectors are on the line, then what happens, its subspace is this point only. When all the vectors in a plane are situated in a line, then its subspace is the point. When the vectors are lies in the entire plane, then its subspace we consider as the straight line, and definitely that straight line lies on the plane and has to be passing through the origin, because in the definition it is given that the vector subspace never be an empty space and it will contains the vector 0, 0. So that is essential. Similarly, if your vectors are on the 3D, three-dimensional space, then its subspace is the plane passing through the origin. Any plane passing through the origin will be its subspace. I'm showing here the some standard subspace. So any matrix is there and its projection, suppose we want to find out. So any matrix, for if we want to find out its projection, suppose it is a 2D matrix and there are the different vectors. So projection means any vector, suppose this is the tip of a vector and its projection, if we want to find out, then it is the tendency, not tendency, it is the actually it is the concept of the projection, that from this point, if we if the projection is required on this line, then from this point we should draw the perpendicular on that plane, and at that perpendicular point we will get the projection of this point. So that is the concept, and that's so why whatever the vectors are there, all are projected in the same line. So this one is the projection matrix. And one very beneficial thing of the projection matrix is that it will goes from higher dimension to the lower dimension. So it will reduce the dimension. So till that, we will find out different matrices. Now come to the inverse matrix. That is also a very important one. So in inverse matrix, in point of view, the transformation is very important, because here the just have a look. We know the inverse matrix means A inverse into A is the identity matrix. That means what? If for a vector, any vector, suppose it is V, if we multiply with the matrix, then we will get a transformation. And if we multiply with this one, the A inverse, then what happens? If we multiply with this one, the A inverse, definitely we should get back the vector V, because A inverse A is the identity matrix, and we know that I into V, there is no change in the vector V, and it will give us the vector V. That I hope everybody know. So here the inverse matrix calculator. So if this one is a matrix, its inverse matrix is 2002. You can calculate, you will find out that its inverse matrix is this one, and accordingly, if this one is the transformation which we shall apply on a vector, this one is the scalar transformation where the x-axis squeezes. So if we apply after this transformation the inverse transformation, it will get back its original position. Similarly, if we apply the rotation here, the rotation means it is the orthogonal transformation. If we apply, then it will definitely rotate, and after this rotation, if we apply the inverse matrix, then it will rotate back. So basically, inverse matrix means it is the untransformation, we can say. So for any undo, invert or revert, we apply the inverse transformation. So till that, what we will find out, the different kind of matrices, the identity matrix, then the scalar matrix, then the identity matrix of by one, then the negative entries with the identity matrix, diagonal matrix, square matrix, sphere matrix, orthogonal matrix. So various kind of matrices and its geometrical view. If it used as a transformation, then what will really happen? Here it is. Next to is the projection matrix and invertible matrix that we will find out here, and these are the very important. Here the diagonal matrix and the orthogonal matrix, these two are very important. We know that the diagonal matrix means it will just stretch the area, and rotation, that is the orthogonal matrix, is the purely a rotation. So that you know. So now from here onwards, so I can say that after knowing all those matrices, our goal for the next part of the lecture is to look at any matrix, basically any symmetric matrix, and trivially says it is the transformation may be visually complicated by using spectral decomposition. So any matrix you have, and we want to find out its transformation. Any matrix means any square matrix, any rectangular matrix, anything it can be, and what will be matrix. I hope I'm audible. Is there any problem? Hello? Is there any problem? I hope I'm audible. Am I audible to you all?
Yes, ma'am, you're audible.
Okay. So now our goal is to find out for any matrix what should be the transformation, either directly or indirectly, better to say. So just have a look here. So the term transpose, okay, first of all, this is the symmetric matrix. And everybody know that a symmetric matrix means it have the property that AJI is equals to AIJ. And this one is a non-square matrix. Symmetric matrix always be a square matrix, and it is a non-square matrix, and non-square matrix is never be a symmetrical matrix, that everybody of us know. So now the term transpose by itself does not refer to a matrix, but rather transpose is an action that can be performed on the matrix, which is to take the rows of a matrix and take them the column instead of instead of 10 times, we call the resulting matrix a transpose or transpose of a matrix. Just we write down the rows into columns and the columns into the rows. And the very magical thing is that this is the square matrix, and in the square matrix, if we write A as a transpose, then we can write it. And if it is the symmetric matrix, then A and A transpose becomes equal. That means A is equals to A transpose if it is a symmetric matrix. But suppose you have the non-square matrix. So if it is a non-square matrix, suppose this one is a 3 cross, this one is a 3 cross 2 matrix. And if we take the transpose of 8, that is R3, then it becomes 2 cross 3. So these are two definitely different things. Here the dimension will change. So here, if we symmetric matrix, that I told you that symmetric matrix means S is equals to S transpose. But if it is the orthogonal matrix, in orthogonal matrix, for what happens here, if we take the transpose of an orthogonal matrix, then its transpose is just its inverse. That means Q inverse and Q transpose are the two same things. So from here, we can say that the orthogonal matrix produces rotation transformation, and the inverse of a matrix means untransformation. The untransformation of rotation means rotation in the reverse direction. The transpose of orthogonal matrix is also the inverse matrix, and the transpose of orthogonal matrix means rotation in the reverse direction. Now we are come to the point to understand the matrix decomposition, because I told you that our goal is to split any matrix into the easier transformations. So this is called the matrix decomposition. So if we understand the matrix decomposition, so previous to that, it is the matrix composition. So matrix composition already we know. So that is, just have a look. This one is a diagonal matrix, and that we can compose in terms of these three matrices. So that we know. So the matrix decomposition is essentially going in the reverse direction. So here composition means multiplication of some matrix to the one matrix, and decomposition means one matrix is multiplied to some, that means more than one matrices. So our target, I hope you know that it is the matrix decomposition, how to get the matrix decomposition. But before that, few more terms which is very much required in the linear algebra, that is the determinant. And what is the determinant? That I already told you a little bit, I think. But still, suppose this one is a matrix and the two vectors are there. One is the 3, 0 and another one is the 0, 2. So 3, 0 means this point, and 0, 2 is this point. So this vector and this vector, here just the green line and the pink line. So this one comprises this area, and this area is what? This area is the, we know this is the base, that, or this is the length, and this is the width. So according to, it is the 3 cross 2 is equals to 6. So this is the area of this entire covered portion. And how to get this one? Very simple. If we take the determinant of this matrix, then it is 6. So this is the area. So determinant always prescribes the area of a place. Similarly, suppose this one is your matrix. If this one is your matrix, so then 1, 0 is this matrix, and 1, 1 is this matrix. So the area is what? The determinant value. Here the determinant value is what? It is 1. And now just have a look. This one is nothing but a rectangle, yeah, that is parallelogram. So here, if as it is the parallelogram, so just we know the area of a parallelogram is the base into height. So base is this one. So this is 1 unit, and height means, here just have a look, from this point to this point, if we draw the line, so this is the perpendicular and this is the height. So this is again 1. So that the area of this parallelogram is 1. Suppose this one is the determinant, and similarly for this determinant the area is 6 unit. And suppose this one is again another determinant. So here also the area we can find out. That means whatever be the vectors enclosing the area, that we can find out very easily. So these all are now here. If suppose the determinant value is 0, If determinant value is 0 means what happened? It is essentially two vectors are linear. Because if the two vectors lies in the same line, then only we can find out that determinant value is 0. So that is the significance of the determinant. And if suppose the determinant value is negative, negative means what? Area is negative? No, definitely no. But this negative means it is the direction where the area lies, in the positive quadrant or in the negative quadrant, that it will depict us. So if it is the three-dimensional case, and suppose it is a three-dimensional matrix and the determinant value is the 0. So if it is so, that means the columns must be linearly dependent. Otherwise, this value never be 0. And this is the, suppose our matrix is given where only the diagonal entries are given and off diagonal entries are 0. And if you want to find out the determinant value of this one, then very obvious. We know how to find out. It is this multiplication. So a into d minus of 0. So this is, we can say, the formula to find out the determinant value. And the area means this is a perfect rectangle, and the area of the rectangle means we know that is the length into breadth, and that is so. Suppose there are three terms added in the matrix, so a, b and 0d. So again we will apply the find out the value of the determinant means AD minus B into 0. So again it will live with the AD only. So AD means A is the base and D is the perpendicular distance of this parallelogram. So this is the formula you can see. Now come to this determinant. Here all four values are given. Then how to find out, that is what should be the formula. So when all are non-zero entries, that time what happens? These are the two base vectors. These are the two base vectors. Okay, these are the two base vectors, and its area definitely we shall find it out AD minus BC, and this is the explanation that how it will be getting. So this is the determinant about, and the linear system of equation. Without the linear system of equations, the linear equation or linear system will be incomplete, I think. So this one is a linear system of equations. So in this linear system of So this one is a linear system of equations, and here, so usefulness of the matrix is to find out the unknown variable. In this system, x, y, z are the unknowns, and we can write this one as the ax is equals to v in this format. So now, here ax is equals to v. This is the system of linear equations we represent. Here, what actually we do? Here, x is the unknown. We are going to find out this x, and v is a vector given in the space, and we shall find out all those vectors for a fixed transformation which will go to the vector v. That means this one go to the vector v. So that is our target in the linear system of equations. So what happens actually? So the whatever be the answers for this linear system of equation, that is we find out in the column space. And if you have the equation like ax is equals to 0, so that is we will find out in the null space. Its answer, that means all x values are lies in the null space, which is also termed as the kernel. So this is the transformation. Inverse transformation that everybody know that if we do the inverse transformation, that it will gives us the identity. So accordingly, this one x means we have the vector av is equals to ax is equals to v. So that from here the x we should find out just by in this formula. So that is just geometrical. Its interpretation is given over here. So now the rank, and rank is again, I hope everybody knows, is very important. So rank means what? Any matrix for any matrix is given. So that matrix for rank 1, if it is, then we can able to multiply, or we can find out that the rank 1 matrix can be decomposed into 2 matrices of rank 1. Similarly, if rank 2 is there, that means for any matrix the rank is 2, then we shall find out the decomposition of two matrices when we will discuss the spectral decomposition. That time we will get this much clear. So this is the full rank. I hope everybody know that the full rank means the number of column is the number of rank, then it is the full column rank. And if the number of rows in the given matrix is the number of is the rank, then it is called the full row rank of the matrix. And for the system of equations, for the solution of the system of equations, this rank is very much essential, because in the matrix equation with m is equals to n, that means number of rows and the number of columns, if these are equal, and A is the full rank. A is the full rank means the number of m, that is m and n both are same, and that is the rank. That means the matrix is non-singular. Non-singular means its determinant value is not equal to 0, and that time we have the unique solution. And if it is not the full rank, then there are two situations occur. One is the inconsistent system where the no solution we shall find out, and another one is the consistent system but with the infinite number of solutions. Now the two very important thing, that is, one is the eigenvalue and another one is the eigenvector. So now eigenvalue and eigenvector, for everybody of us know that we can multiply it as AV is equals to lambda V. So A is the matrix, V is a vector, lambda is A is the linear transformation definitely, and V is the eigenvector we can say, and the lambda is the eigenvalue, and V is the original direction. So this one from, actually what happens, eigenvalue means what? In a space, any vector after transformation, if it will not change its direction. Remember, if it will not changes its direction by any transformation, then that particular vector is called the eigenvector. And by this one, AV is equals to lambda V, what does it mean? That A is any transformation, linear transformation, it will apply to a particular vector. A specific vector is there. After applying this one, the vector remains unaltered. But what will be the change? Only change a scale, only change by the scale. So this vector V is called the eigenvector. And how much it will extend it or it will squeeze, that value is the eigenvalue. So how to calculate the eigenvalue, I hope everybody know, but still I'm just discussing a little bit of it. Suppose this one is a matrix and we want to find out its eigenvalue and corresponding eigenvector. Then we know the formula is A minus of lambda I, and we should take its determinant value and make it to 0. So if we will do so, then from here it is 1 minus lambda into 1 minus lambda, then minus of 4 is equals to 0. And after solving, we shall find out there are two values of lambda we shall find out. One is the 3 and another one is the minus 2. And the corresponding to 3, we calculate the eigenvector, which is 1, 1, and corresponding to the V, that means minus 1, we get the eigenvector. It is the minus 1, 1. And how to calculate for that, I hope not to say that much. It is the lambda I, we know with that the x and is equals to the 0. If we do this equation and after solving, whatever be the x values are there, that are gives us the eigenvector. So this is the eigenvector. And now what happens here? So just have a look. If we multiply the matrix A with one of the eigenvector, this is the eigenvector V, then after this multiplication we get back the eigenvector but with 3. That means we actually get it as 3, 3. And similarly for the second one we will get so these are the values. So we can say that the after any linear transformation on the eigenvector, it will not change after the transformation even. So now one very important thing is the positive definite matrix. Why I am coming to this positive definite matrix? Actually, our target is to decompose a symmetric matrix into the some simpler matrices. So this is the part of SVD. singular value decomposition. So I'm coming to that part. If you know this is VD, then for that the positive definite matrix is also very important. So what is the positive definite matrix? So positive definite matrix means now you all aware of the eigenvalue, eigenvector, determinant and everything. That's why here the positive definite matrix means it have few properties. It have few properties. So that first one is positive definite means all the positive definite means all the eigenvalues are greater than 0. All the eigenvalues are greater than 0. All the eigenvalues are greater than 0. So now here it is the first case, it is the all the eigenvalues are 0. Second one, a matrix is said to be positive definite if we shall find out x transpose Sx is greater than 0 for all x not equals to 0. This one is a very important part in the data science actually, and this is called the energy equation. How it will work, I'm trying to explain it a little bit. And there are another criteria also to say matrix is a positive definite matrix is S. That means A transpose A. If S is and can be written in this format. This format means any matrix if can be written in this one and this is a symmetric matrix, then it is positive definite because for any symmetric matrix all the eigenvalues are greater than 0. Next, it is the all leading determinants greater than 0. All leading determinants are greater than 0. What is leading determinant? That I'm going to tell you with an example. And the last one, the last criterion is the all pivot in elimination greater than 0. All pivot in elimination is greater than 0. So how to explain these three with the example? Let us experience. So just tell me if suppose your matrix is here 3, 4, 4, 5. So is this a positive definite matrix or not? So first of all, we just find out the determinant value of this one. So its determinant value is, it is 15 minus 16, which is minus 1. So just have a look. We have here the all leading determinant greater than 0. And we shall find out here the determinant value is minus 1. So minus 1 means one of the determinant value is minus 1 means it is not a positive definite. By the way, the leading diagonal means what? Let me tell you. Leading diagonal means if we consider this corner, this is the 1 cross 1 matrix. This one is one of the leading diagonal. Then the leading diagonal matrix. Then next, as it is a 2 cross 2. So the 2 cross 2 means all 2 cross 2 matrix from the cornermost, the principal most matrix we consider, and if its determinant value is not equals to 0, then we say this one is the leading determinant. So leading determinant we come to know if it is the third order, then accordingly the 3 cross 3, the first corner 3 cross 3 matrix is the leading determinant. So accordingly, if these determinant values are not equals to 0, then the matrix is positive definite, but it is not so. But suppose if we give a little bit change over here, our target is to make the determinant value is positive. So that if we convert it to the 3, 4, 4, 6, that means if we change it into the 6, only this 5, if we convert it to the 6, then what happens here? If now we find out the determinant value, then it is 6, 6 3s are 18, then minus of 16. So this value is 2. So this one is the positive one, and then that's why we can say it may be a positive definite matrix, and definitely we shall find out its we can find out its eigenvalues, and if we shall if we can find out those eigenvalues are the greater than 0, we can say positive definite. Rather than here also, from here also we can say that as it is the positive, and this one, the 2 cross 2 matrix is also positive. That's why we can say it is the positive definite matrix. And now suppose the another matrix is here where I have taken the minus 3 and minus 6 only. So this is the third matrix, but this one is not a positive definite matrix. Why this is not positive definite? Because here the leading determinants are non-positive. Is it not? Because here it is the -3, which is not positive. Regarding the pivot, I also can tell you, if on the basis of pivot you want to justify the positive definite matrix, then you can find out that the pivot for, suppose we find out the pivot for this one. So it is the way to find out is that the 2 cross 2 determinant divided by the value of the 2 cross 2 determinant divided by the value of 1 cross 1 determinant. If it is greater than 0, then it is called the positive pivot. So it is the 2 cross 2 determinant value is it is 2, and 1 cross 1 it is 3. So the value of this ratio is 2/3, which is definitely greater than 0. So from here also we can say it is the positive definite. One more thing which I want to tell you, which is I told you na energy equation, that is x transpose a matrix, suppose S, and then X. If this one is greater than 0, then it is the positive definite. So just let me explain a little bit about the energy equation. This is called the energy equation. So S, suppose it is a this one is suppose a second order matrix only. So let it be same matrix, this one 3, 4, then 4 and 6. Let us consider this one. Now for the x is any vector, suppose it is xy. Actually the vector is xy and we have taken its transpose. So now if we multiply this entire thing, then what we shall find out? After this entire multiplication, we shall find out 3x square plus 8xy plus of 6y square. So this one is nothing but a function of x and y. So this one is an energy function. This one is an energy function. In big data handling, by minimizing this energy, we can find out or we can handle the data, or we can manage the data, as you can see. And why this, and this one is greater than 0 means what? If we just take the pictorial representation, suppose this is the x-axis and this is the y-axis, then f of xy we can do in towards this direction. Then this equation, this equation, if we get like a bowl, we just get like a bowl. So this one, so the bowl as much, that means depending upon this structure, we will find out that how strong energy is here or how less energy is preserved over here. So I'm not explaining much, because again from here there is so many things to explain. So I'm not explaining that much from here. But anyways, this energy equation is very, very important. And this energy equation, by maximizing or minimizing the energy equation, we shall find out so many hidden components for the data science. So next it is the spectral decomposition. The name I have written here, spectral decomposition, but of course it is the eigenvalue decomposition. It is nothing but the eigenvalue decomposition, and eigenvalue decomposition is said as the spectral decomposition. So here it looks like a matrix is given here, and the Q, then it is the sigma and Q transpose. Here this is the linear, this linear transformation is, this is the eigenvalue, and this is the corresponding, this is the eigenvalue, and this is the corresponding eigenvectors. So we know that if the transpose of a matrix we have considered, then it is orthogonal. And of course, let me tell you that S we have taken here the symmetric matrix, because our target is to apply linear algebra in data science. And in data science, we always target it to take the matrix as the symmetric matrix. So how to do that? That also I will tell you. So here just have a look. The orthogonal matrix is this one, and this is the diagonal, and this is again the orthogonal. So, and the eigen decomposition for, we know that AV is equals to V. That means this is the eigen decomposition that everybody know, that any matrix we can diagonalize in this way, and this is the eigen decomposition. So I'm not explaining the much for the eigen decomposition. So here just have a look, eigen decomposition. So well, let us directly come to the SVD, because I think time is half an hour left. So I have lots of things to tell you on the SVD. So here the SVD is the eigen decomposition. You know that how to do the eigenvalue decompositions. One very vital thing is that whenever we do eigenvalue decomposition, is we shall deal with the square matrix. I hope all of you agree with me. But whenever we are coming to the SVD, that means singular value decomposition. Remember, first one is the eigenvalue decomposition. Now we are coming to the singular value decomposition. So in the singular value decomposition, the not necessary that the matrix is a square matrix. If any non-square matrix you have, then also we can do this one quite easily. So for the SVD, what the things we know, that is the range, null space, eigenvalue, eigenvector, transpose, inverse, symmetric matrix, orthogonal matrix, and PSD matrix. What is PSD? That is the semi-definite matrix. That means positive semi-definite matrix is this one. We know now what is the positive definite matrix. So now positive semi-definite is what? That is very simple. If your lambda I not strictly greater than 0, but it is greater than equals to 0, then it is positive semi-definite. So using this SVD, we have the different things to do. And SVD, if once you come to know what is SVD and how to apply this SVD to the any matrix decomposition, then there are various kind of decompositions exist that for you can get understanding and you can apply your that is at first you should know the SVD, then only you can apply all other decomposition in the SVD, and you can find out or you can get better idea about all those other decompositions. So here the various decompositions I have written. So all these are exist. You can go and verify all those decompositions, and in the data science point of view, this decomposition is very, very important. So now here I have written A is any matrix. So there is no restriction on the matrix. It is symmetric. It is that means regarding the dimension there is no restriction. Regarding the rank there is no restriction. So matrix is symmetric. It is also not required. It is also not required that any matrix you might have, that matrix we can decompose into three parts. That matrix we can decompose into three parts. So here, first of all, any matrix, suppose it is 1, 2, here it is given, and any matrix 1, 2, 3. Can you tell me what is the difference between these two matrices? What is the difference between these two matrices? Yeah, of course, if you just want to look, that means you want to visualize, then we can say that our Earth, which is like a globe, so that is in 2 dimensions we can say, and if we just take it as a disk simple, then it is in the 2 dimension. Here, Z, though X entry, Y entry, both are same here, and Z entry is 0, though there are no significant changes over here, but the third dimension is here created. If someone asks that what about the z-axis, then its answer is 0. But if your matrix or your vector is in the 2 dimension, then you can say that the vector, that means this one is only in the 2 dimension, and regarding the z dimension there is no information. So that just think of, you have a square matrix, that is a non-square matrix. So this one is a non-square matrix. So this non-square matrix, if you multiply this non-square matrix by that means this non-square matrix from, this is a 2 cross 3 matrix. So that with we can multiply that means the if we multiply a vector of 3 dimensions, suppose this one, here it is given. So if we multiply, then it will gives us this one. So that the dimension eraser you can see here. So just come to the dimension eraser. Suppose this one is again a 2 cross 3 matrix. So in this 2 cross 3 matrix, if we multiply or if we give this transformation, then what happens? All these are the 3D objects because there are the 3-dimensional structure, X, Y, Z, all the 3 axes are there. So if we apply this transformation, then what happens to this one? This one is a cylinder. It will becomes a just a circle. If this one is a cuboid, then it will becomes a square, and this a pipe, and that will just giving you a hollow structure, hollow circle structure. So if you just apply this type of matrix, then what happens actually, though there are x, y, z, all the three values are there, but after this transformation, we will get it into the two-dimensional state. So we will reduce one dimension here. Similarly, it is a dimension adder also. In the dimension adder also, non-square matrix can be used. So if this one is a matrix, this is a 3 cross 2 matrix, and if we multiply with that a vector of 2 dimension, then what we shall find out, the resultant will be a 3 dimension in, and any second dimension, that means these are drawn in the 2 dimension, but a z axis will be included over there, though it is a 0, though the value of the z axis is 0, but the structure is in the 3 dimension. So just have a look. It is a 3-dimensional matrix. It is a 3-dimensional matrix, and if you multiply a matrix here, not 3-dimensional, it is 2 cross 3 matrix. So non-square matrix is given A, and if we just simply take transpose, and after that, if we multiply these two, then what happens? Definitely, we shall find out this matrix. Yes, and if we do the reverse, then what happens? It is first we have taken the A transpose, and after that A, and if we multiply, then we shall find out A transpose A. Then very obvious, this is the given matrix. This one is your A. This one is your A transpose, A transpose, and this A transpose, and this one is your A transpose A. And these three are 3 different matrices. Now, one very magical thing you should observe, if we multiply A transpose, then we shall find out a 2 cross 2 matrix, and it is symmetric matrix. It is symmetric matrix. And similarly, if we multiply A transpose A, then we shall find out a 3-dimensional matrix. And is multiplied by a transpose, then we shall find out a symmetric matrix. That is a very vital thing which we have. So what happens for it is the 2 cross 2 matrix. So in this 2 cross 2 matrix for which is our A transpose, is for this one we shall find out the 2 vectors, and these vectors are not termed as the eigenvectors, these are termed as the singular vectors, because this is a singular matrix and its eigenvectors, but we shall find out these are the singular vectors. So for this A transpose, which we shall termed as the SL, SL means left singular, so its eigenvectors we shall find out as the, suppose it is u1 u2, and this is called the left singular vector. Similarly, SR is the right singular vector, and this one is your nothing but A transpose A. So what happens here? We shall find out A transpose A and A transpose from the same matrix A, so that what is the eigenvalue of this one and what is the eigenvalue of this one? Are they same or different? Definitely, as this one is a 2 cross 2 matrix and this one is a 3 cross 3 matrix, here we have the 2 eigenvalues and here we have the 3 eigenvalues. Then what happens? Suppose here the eigenvalues are lambda 1 and lambda 2, and here the eigenvalues are lambda 1, lambda 2 and lambda 3. Then what happens here? Here the positive definite, that concept will come to the action. That here what happens? The among these two, definitely there is greater than, that means suppose lambda 1 is the greater than lambda 2. So there's 2 distinct eigenvalues we shall find out, and here also the 3 distinct eigenvalues we shall find out. And among these two, which one is largest? Suppose lambda 1 is largest, that one should be equal to the eigenvalue of the among these 3, which one is largest. Suppose lambda 1 is the largest among here, so that the lambda 1 from this one and lambda 1 from this one should be same. Next, the lambda 2 if we consider, and lambda 2 of this one should be equals to the lambda 2 of this one. Then what about this lambda 3? So whatever be the eigenvalues of the matrix A transpose A and whatever be the eigenvalues of the matrix A transpose, both are definitely same. But what about all the extra eigenvalues? If it exists, then these all extra eigenvalues are 0. So here lambda 3 should be equals to 0. So what happens actually? Here it is a matrix and eigenvalues we have calculated. So these are the lambda 1, lambda 2 eigenvalues. We have written this extended one because if extra eigenvalues are there, then we may write it down in the next row, but all the entries are 0, so that the effective portion is only that much. So anyways, so on that respect to this one, we can definitely find out the we can find out the singular vector, that is for A transpose and for A transpose A. We can find out all those vectors definitely. So accordingly, these are the singular vectors we shall find out, and this is the singular values we shall find out, and based on this we can decompose this one. And if we will take the reward one, then this is the form. The same thing here in previous one, we have taken the 2 cross 3 matrix, and in the next one it is a 4 cross 2 matrix. So accordingly here the 4 that is the 4 singular vectors are there, and here definitely 2 singular vectors are there, and eigenvalues are 2 only. Very obvious, because the lower dimension always define that how many distinct eigenvalues are there. So visual impact, so SVD means it is actually rotation, then dimension adjustment, then stretching, and again then rotation. So this is the visual effect, and why I have taken this one, that I can relate with the data science, that in data science what happens, we have a huge data, and that huge data, suppose thousands of data are there, or here it is given that 20 of data are there, and for those 20 data we have only 2 attributes. For those 20 data, we have only 2 attributes. So it is 20 cross 2 matrix is there. So this is a non-square matrix. If that type of matrix we have, then using the SVD, we can have the insight of the analysis of these data very easily, because we can reduce one of the matrix as 2 cross 2, a second dimensional matrix only. So we can reduce the data in that way. So just come to the next, is the singular value decomposition. How to, here A is equals to U, then sigma, then V transpose. I'm telling you again and again, but how these things will we find it out, that we will discuss later. So now here just have a look. Here the A transpose A, I told you we should do the A transpose A. So how to get that, just have a look. A transpose A means it is U sigma V transpose. Then A transpose A, if we substitute the values, then we shall find it out this one. And if we simplify, here just have a look, this one means it should be V transpose, sigma transpose, then U transpose. So it is V, not transpose, because already transpose is there. So it is V sigma transpose, then U transpose. And here it is U, then sigma, and the V transpose. So this part is identity. This part is identity. And then it is sigma transpose and sigma, both are the eigenvalues, so that instead of that means the transpose and the sigma both are the same matrix definitely, so that we shall find out it is the sigma square. So we find out this one. After getting this one from here, it is very obvious that if suppose A transpose A is a matrix C, A transpose A is a matrix C. So C into C into, suppose it is W is another vector, we know it is equals to lambda of W. It is from the eigenvalue decomposition or the spectral decomposition that we can do. So if it is so, then what we will find it out from here, that this sigma square is nothing but the eigenvalue of this one, and V is the corresponding eigenvector of this one. So here it is the complete visualization. Just have a look. This one is the symmetric matrix. We know that this one is a symmetric matrix, and V is the orthogonal matrix. Always for the symmetric matrix, whenever you find out the eigenvalue, it will comes as a symmetric matrix. Then it is the square of the diagonal matrix. Square of the diagonal matrix means for the matrix A, the eigenvalue, if it is sigma, then A transpose A for the eigenvalue denoted by that sigma. So whatever be the eigenvalues, you shall find out, and for A, if you want to find out the eigenvalues, if its eigenvalue, suppose one of the value is sigma 1 here, sorry, sigma 1 is the one of the eigenvalue from here, then for the matrix A, the eigenvalue is this one. Anyways, so these are the form. Then similarly, the V also we can find out if we multiply A transpose. That means if we do the reverse one, previously we will do A transpose A to get the V, and now we will do A transpose to get the U. So A transpose, we get the U, and just this is the comparison. Now just have a look. This is the transformation. What happens? This one is the matrix form is given, and it will goes up to this one after the SVD. After the SVD. So SVD means if you do at first this transformation VT, and after that this that eigenvalue multiplication, or the singular value multiplication, better to say, and from there if we multiply U, then at the final you get this transformation. So we will visualize actually from here to here, but this is the in between steps. So I told you about the SVD, but one more thing, that how to get this SVD properly, that it is very difficult to calculate actually. Suppose a matrix is this one and you want to decompose it into the U, sigma and V transpose form, then what are the steps? Here are the 7 steps to get this matrix in this format. So I'm just explaining one by one the steps. So the first step, I hope you understand that at first we shall calculate A transpose. After calculating this one, from there we find out the eigenvalue for A transpose. So here we shall find it out as 10 and 12. And here the corresponding eigenvectors, I have find it out in this way. I have not calculated this one, but I'm telling you, you can calculate by yourself, because if this one is a matrix and then its eigenvalue and eigenvector is easy to find for you. And this one, A transpose A, again we find it out. This is a 3x3 matrix, and definitely there are 3 eigenvalues we shall find out, and the corresponding eigenvectors we shall find out in this way. So now U is the matrix this one, then V is this one, and sigma is this one. But how we shall find it out? For that, U is this one. I told you that as this is a symmetric matrix, then its eigenvectors are orthogonal. So orthogonal means their matrix multiplication gives us, that means their multiplication of these two vectors, or the dot product of these two vectors, gives us 0 value. What we will do, we just at first make these vectors normalize. Normalize means here this one and -1 is given. So if you want to normalize this vector, then we should divide this 1 by √2 and this -1 also by √2. So now it is a normalized vector. So it is orthonormal vector we convert it to. And here also we just converted it by dividing the √2. Why we divided √2? I hope you know that the first entry is 1 square, then the second entry is -1 square, and then its root. So that it is 1 plus 1, so it is the √2. So in that way we find out this √2, and we will convert it into the orthonormal matrix. And similarly for this also, so here the orthonormal, if you want to convert, then it is the 1 plus 4 plus 25 and its root, so that it is 30. So root over of 30. So we should divide this one by √30, this one also by √30, and this is also by √30. Similarly from here, if you want, then it is divided by √5, and it is also divided by √5, and here also it is 6, root over of 6. Here is also by √6, and here it is also by √6. So just have a look by dividing in that way, and this is it. Of course, after transposing we write down. And one more thing, let me tell you that here the eigenvalues are 10 and 12. Among this one, 12 is the larger one. That's why while we constructing the U, at first we write down the corresponding eigenvector of this matrix, that is 1 by √2 first, then 1 by √2, and after that it is 1 by √2, then minus of 1 by √2. Okay. So just have a look. I have written this one and get this one. And similarly for V, I just write down in the similar way which one is the largest eigenvalue. Corresponding to that, I write the vector make the vector as first column, and the second largest for the second column, and the third largest for the third column. So we shall find out this one as the corresponding V. And the sigma, I told you that sigma means what? Sigma means it is the root 12 and root 10. Why? Because we find out the eigenvalues for the matrix A transpose or A transpose A. But our requirement is the vector for the matrix A. And so how it will come, that can also be explained, but right now the time is less. So anyways, so here this one is the combination. So A is the matrix, this one we shall find it out. One more thing here, just let me tell you, we just left the rank behind, I think. So if we multiply this matrix, so that suppose this one is your U1, this one is your U2, this is U1, U2, and this is your sigma 1, this is your sigma 2, and this is your V1, this is your V2, and this is your V3. So we just separated it by sigma 1 U1, then V1. Then similarly, next it is um, sigma 2 U2 V2. In this way, we can combine this matrix and just have a look. All of these are the matrix with rank 1. And one more magical thing is that this term, here, there is a speciality. I have taken the first column of this vector as the singular value, which is the highest singular value corresponding to that column. This one is the highest singular value, and this one is the again corresponding to the highest singular value, whatever the singular vector. So when we multiply, so that term definitely is the leading term. So that term is the leading term. So from here, the principal component concept will be their PCA. So that one is very much important, and that one that means that one carries a lots of information about the data in the from the heap of used data to analysis. So from this SVD, if you know, so from here it is the PCA, and the all other techniques you can easily find out. So this is, I'm not explaining. So now this is the time for application part, for I can say you that this SVD is used in the recommender system, dimensionality reduction, in the image compression. We know the JPG images, so that will be squeezed. So this image compression in the SVD is used, dimensionality reduction in SVD is used. In recommender system, recommender system means there are various platforms, you can say the social media and all, they will recommend us the different things, or in the e-commerce, Amazon, Flipkart and all, based on our purchase they will recommend us the different things in the Facebook and Twitter. Based on our searches they will recommend us the different search things. So how this recommender system will work, that also we will find out from the linear algebra, if you apply this linear algebra. Beyond that, the text mining, social network analysis, and the natural language processing, there are lots of areas where we can apply this linear algebra, this knowledge of linear algebra. Though it is a very vast thing, but it is very difficult to sum up within this 1.5 hour lecture. But still, I try my level best. And I'm not explaining this all because these are the few case studies on based of the different application parts, so image compression algorithm and all, and few different techniques which you can apply over there. So these are, I'm not explaining. So these are the different algorithms, and here is the conclusion that the linear algebra is a fundamental and indispensable mathematical framework in the field of data science. It serves as the backbone of a wide range of data manipulation, analysis, and modeling techniques. Linear algebra serves as the bridge between raw data and actionable insights in data science. Proficiency in linear algebra is essential for data scientists as it empowers them to understand, manipulate, and model data effectively. Whether we are developing advanced machine learning models or conducting exploratory data analysis, a solid grasp of linear algebra is a valuable asset in the data scientist's toolkit. So these are the references, and that's all for my topic. So if you have any question, then you can ask me now.
Thank you, madam, for this wonderful session.
Yeah, thank you, ma'am.
Welcome, ma'am. I think so. No any question from. If anyone has any question, please feel free and ask the question. No one can respond. So thank you, ma'am, again. And
I just want to ask the audience that is it beneficial, or do you think that it is a little bit helpful for your future endeavor?
from our side, we can say everything is very fine.
Anyone from the audience, I want to hear. If anyone. Okay, so there are Purinita Dotto and Ranjan Banerjee and say that yes, ma'am, it is helpful. So thank you.
Okay, thank you, ma'am, once again.
Okay, thank you.
Welcome.